Have you ever dropped something and noticed how it always falls downward? Whether it's a feather or a stone, everything is pulled toward the ground. But have you ever asked, why downward and not sideways or upward? That invisible pull is called the force due to gravity. It is the same force that keeps the moon revolving around the earth and the earth around the sun. Now, on earth, gravity pulls every object toward its center. This pull always acts vertically downward and is strongest near the surface. When the height from the Earth's surface is very small compared to Earth's radius, we assume this pull, or force, to be uniform, the same for all positions near the ground. This force acts from the object's center of gravity and is directed toward the center of the Earth. Let's understand how we mathematically describe this force. The force due to gravity depends on four things: the mass of the object, the mass of the Earth, the distance between their centers, and a universal value called the gravitational constant. This gravitational constant is a fixed value that remains the same no matter where you are in the universe. Its value is approximately 6.67 into 10 raised to the power minus 11. The mass of the Earth is roughly 5.96 into 10 raised to the power 24 kilograms, and its radius is about 6.37 into 10 raised to the power 6 meters. With all these, we can now compute how strong Earth's pull is on any object placed near its surface. Let's apply the formula to a practical case. Finding the force on a 1 kilogram mass, we take the values we discussed: gravitational constant, Earth's mass, radius of Earth, and the object's mass, and plug them into the expression. When you carry out the calculation, the result comes out to approximately 9.8 newtons. This means the Earth pulls 1 kilogram of mass with a force of 9.8 newtons straight downwards. This number, 9.8, is extremely important in physics. It is why, when you let go of something, it accelerates downward at about 9.8 meters per second squared. Now let's talk about direction. The force of gravity always acts toward the center of the Earth. It's consistent no matter where on the surface you are. Here's an interesting insight from Newton's third law. If Earth pulls on a body, then the body must also pull on Earth. Yes, the object also exerts an equal and opposite force on Earth. But why doesn't Earth move? It's because of inertia. Earth's mass is so huge that this reactive pull doesn't cause any noticeable movement. So while you fall toward Earth, Earth technically moves a tiny bit toward you too, just too little to notice. This pair of forces perfectly represents an action-reaction relationship in nature. Now here's a fun twist. Gravity is not the same everywhere. Different planets have different masses and radii. This means that the gravitational pull they exert on objects varies. For example, the moon has less mass, so the same object weighs much less on the moon. This is why astronauts on the moon can leap much higher. The pull is weaker there, but no matter which planet or moon you are on, the law of gravity remains unchanged. It always depends on the product of the two masses and is inversely related to the square of the distance between them. So whether you are on Mars or Jupiter, gravity still works, just with different strength. So to sum it all up, force due to gravity is the invisible hand that holds us to the ground. It's a universal interaction between any two masses. On Earth, it gives everything weight and pulls objects down, with a nearly constant force of about 9.8 newtons per kilogram. This force explains why things fall, why we stick to the ground, and why planets and moons orbit each other. And it's not just a classroom formula. It's the reason you drop your phone and it hits the floor. I hope now you have a clear understanding of how gravity works at the Earth's surface and why it's such a fundamental part of our daily lives and the universe itself. See you in the next session, where we explore another fascinating idea from the world of physics.